Okay, so welcome everybody to this talk in our LUCI Lunch seminar lectures. And our speaker today is Felix Weitkämper from LMU Munich, where he's a lecturer. He has a PhD from Oxford University on topics of model theory, and his research interests are broadly on connection between probability and logic, in particular logic programming. And today we'll speak about probability logic and statistical relational artificial intelligence. So I will leave the floor to him. Thanks very much for being here.
Thank you very much for the lovely introduction. I'm extremely happy to be here. Thank you so much. I'm thrilled to see that there is a 2-digit number of attendants sacrificing their lunch break. So thank you very much indeed. So I would like to share some thoughts that I've had for a while now about how the traditional approaches to probability logic, going back to Carnap originally and then being picked up by people like Joe Halpern in the 80s and 90s, can help us understand statistical relational artificial intelligence and can help us overcome some of the issues that statistical relational AI is facing today. I will start by giving a short introduction to what statistical relational AI is, what it is about. Then I will give a brief overview of probability logic in its traditional formulations. And then I will sketch an approach as to how one can bring these two concepts together and analyze statistical relational AI from the point of view of probability logic. So I will go back a little bit, and at the danger of boring most of you, to the history of artificial intelligence. So one of the main, and in decades past, the main branch of artificial intelligence is symbolic. It's based on reasoning and on the paradigm that knowledge is derived from facts and rules. Originally, they were handcrafted by experts, and the most important practical incarnation are expert systems. Now, both the facts and the rules involved could, from very early on, be highly complex. It was based on first-order concepts of logic, and that involves intricate relations between different entities. This is a highly expressive way of representing knowledge, but very soon a major limitation emerged, namely that these deterministic expert systems are very bad at dealing with uncertainty. They're bad at dealing with noise, and they're bad at dealing with connections that may or may not hold in every case. So the next framework to enter the limelight was statistical artificial intelligence. This is one of the main present-day machine learning frameworks. The other, which are deep learning and neural network based, I will not go into today. And they are based on statistics and probability theory, which are also old time-honored concepts from mathematics. Now, originally, integrating probabilities into AI was considered impossibly complex because in order to specify a probability distribution, one would have to give the probability of every possible world, and there are exponentially many of those. So specifying this was considered unfeasible. Only with the ingenious idea of introducing graphical models which encode independence assumptions in diagrams did this really become viable. So two of the main frameworks here are Bayesian networks, which are directed and which intuitively suggest causal relationships, and Markov networks, which are undirected and more clearly just express correlations. Now, the main focus when moving into statistical artificial intelligence shifted from complex reasoning tasks to learning tasks. And it shifted from complex specified first-order relationships to simple properties, propositions. Reasoning there is not as complex as it is in first-order logic. Of course, there are various algorithms to do inference in Bayesian networks and Markov networks, but already performant algorithms were suggested quite early in the development, and learning became the main focus. Now, since 2000 and somewhat earlier, statistical relational AI has developed as a separate branch attempting to put these together. So there are two ways to think about this, depending on from which community you originally come. You can either see this as expanding symbolic approaches like logic programming to deal with probabilities, or you can see it as expanding graphical models on the other side to deal with relational information and complex dependencies. Both of these areas are important, and they actually converge in a way in that probabilistic logic programming is actually semantically very closely related to relational Bayesian networks or Markov logic networks, which are the respective extensions of Bayesian networks and Markov networks. So actually it's you can almost see it as a diamond in which probabilistic logic programming and relational Bayesian networks are at the top, and then you have Bayesian networks and logic programs on the reasoning and the statistical side. In this area, as you would expect, both inference and learning are hard because you import all the difficulties from relational and from statistical areas, and they have their own vibrant literatures in all aspects. Major problems here are still unsolved, but there is a strong feeling that it is necessary to combine these areas for strong, explainable artificial intelligence. So let's look at an example of how this would work. So this is a faux formalism. So it's supposed to remind of relational Bayesian networks, but it's really just a template. I don't want to go into the details of syntax and semantics of individual formalisms here. So let's say we have burning houses and we have neighbors of these houses. And the question is, we want to model the likelihood that a call that the house is burning will reach the fire brigade. Now, if we want to do this as a template for all houses symmetrically, we put a variable for the neighbor X or person X and a variable for the house H. And whether someone calls depends on whether he is actually a neighbor and on whether the house is burning. Now, we see if we actually input instantiate houses and instantiate neighbors, this quickly gets quite complicated. So if we so let's say we have two houses and we have two neighbors, Anna and Carla, then whether Anna calls or Carla calls depends on whether Anna and Carla are neighbors and whether the house is actually burning. Now, you see that it would be quite difficult to specify a network like this for dozens of houses and dozens of neighbors. And similarly, we can have smoking friends. This is a classical example from very early in the statistical relational literature called the friends and smokers model, which is used as a paradigm for many things. So we can consider whether the likelihood that someone is a smoker might depend on whether their friends also smoke. So it depends on whether other people are friends and whether they smoke. And again, the more friends there are, the more difficult this becomes to write down. It also becomes difficult to read. So one of the big advantages of statistical relational AI is that they allow representations like this, in which connections are easily gleaned from, rather than representations like this, which are difficult at first sight to understand for a human reader. They're also highly expressive because we have full predicate logic, depending on the exact formalism. You could support high-level reasoning with a deterministic part. And an often overlooked approach is that also, if you learn these representations and you force the representations you learn to use variables, you enforce these symmetries, namely that it should be uniform across houses and across neighbors in learning. So these are all reasons why statistical relational AI is a great idea, and obviously something one should be interested in. However, it has not yet really taken off. And that's because it has two main challenges. One is the high computational complexity. Any most grounded inference method, so essentially brute forcing the calculation by first grounding out to a Bayesian network, say, or by counting up possible worlds in a probabilistic logic programming setting, this will all be exponential in the size of a domain. And that is a problem because we are interested mainly in small templates and large domains. So exponential in the size of the template, the size of the actual model would not be the problem. Exponential in the size of the domain is a huge problem. And actually, without considerable attention, off-the-shelf statistical relational AI solvers struggle at very reasonable domain sizes. So this is a real limitation for everyday use. But the other thing is, we assume that if we see something like this, we can adapt this to many different domains. We learn this model once, we understand its internal structure, and then we adapt it to lots of different domains. However, it's actually unclear how the predictions of the model change as we switch domains. This would normally, in most formalisms, this is the case, and this is why transfer learning is a difficult problem. Moving things across domains is hard. But here it hurts more. It hurts more in statistical relational AI because of the implicit promise that if I have a template specifying a model, the point is to use it in different domains. What's the point of making a template if it is limited to the one domain on which I learned it? So this has got more attention in the statistical relational AI literature than in other transfer learning settings. Because it is seen as some sort of betrayal of the promise of statistical relational AI to its users. So this is the status quo, I would say. Computational complexity has been tackled in many different situations with lifted inference approaches. So there's been work on trying to make approaches which can be tractable in domain size for models of a certain form. And there are plenty of partial results on this. In fact, there is a recent monograph that if someone is really interested in the nitty-gritty details of this, I can only recommend the Introduction to Lifted Probabilistic Inference, which is a recent joint volume. I can give you the details later again as well, in which the technical part of this, the algorithmic part, is tackled in detail. But the TLDR of this, the long and the short, is that essentially we know that it is best case exponential, i.e. it is NP complete or P sharp complete in many general cases. So we have negative complexity results too. So I would suggest a different approach to this that is cognizant to the foundations in probability logic. What do I mean by that? So ever since Carnap in the 1950s, first order logical approaches to probability have already been explored. We have reinvented the wheel in statistical relational artificial intelligence in the sense that there is a large body of work from both mathematical philosophy and computer science that have looked in great detail at these problems. And they've come to the following, a paradigmatic question. If we have meanings to statements such as the probability of a sheep being black is at least 20%, what does that statement even mean? And Carnap passionately defended that there are two different ways of interpreting statements like this. One is the statement about my belief in the color of a certain sheep? Or is it about a statement about relative frequency in an overall population. And he argued that these are two completely different ways of formalizing probability. Now, the first one he referred to as probability 1, and the second one he refers to as probability 2. Now, Carnap is significantly more interested in the epistemic notion of probability, and he devoted a lot of his later life work into understanding it better. And he gives somewhat short shrift to the relative frequency explication of probability. In 1990, the computer scientist Joe Halpern revisits those categories, and unfortunately, he inverts the terminology. He refers to what Carnap calls probability 1 as a type 2 probability. And he refers to the relative frequency interpretation as a type 1 probability. And this is unfortunate for communicating between the two fields. Since I'm currently working in computer science, I use Joe Halpern's terminology, but I think it is quite important to be aware of this distinction and the fact that Joe Halpern is definitely not the first, nor even the one to give the most detailed analysis of this. Now, let's look at the type 1 probability. The semantics of a type 1 logic is defined with respect to a single world, omega. So let's say we have a single structure and a probability measure on this structure. For the sake of argument, we just assume that our structure is finite. We have finitely many sheep, lots of sheep, and we have a uniform probability measure. So every sheep is equally weighted. In that case, if the elements of a structure are sheep and there's a unary relation black, then the probability of a sheep being black is at least 20% is true if at least 20% of sheep satisfy the unary relation black. This is a statement about a single world of sheep. And if I want a model of this situation, I only include the world and possibly a probability measure. And there can be lots of models, all worlds in which at least 20% of sheep are black. The type 2 logic is a bit more difficult to formalize. And that uses what is known as a random world or a possible world. So we take a domain D and we define a probability measure on D. We define a probability measure on the set of structures with that domain. So if we have a domain of sheep and a unary relation black, then the set omega D is the set of all structures on D with a unary relation black, and there are 2 to the number of sheep many of these because it's unary, so we have all possibilities of picking out a subset. And now the probability of a sheep being black is at least 20% is actually underdefined. We need to know which sheep we are talking about. So it can only, if we are talking about epistemic probability, then this has a free variable. And we can only evaluate with respect to a certain sheep X and a certain probability measure on the set of all possible worlds. And then we can say the probability, if mu, the probability measure of the possible worlds, such that black of X is satisfied in that world, is at least 0.2. And now a model is not determined by a single world. It is determined by the domain and the probability measure over all possible worlds. So there's and Carnap argued, and I very much concur with that there is a categorical difference between these two ways of explicating the word probability. And it makes a huge difference for interpreting machine semantics of these. If I want to implement these, on the one hand, my semantics will be defined over a single world. On the other hand, it will define a probability measure over worlds. Conceptually, it is unproblematic to combine these two explications. Carnap notes it as a side remark, and Joe Halpern actually gives this a more detailed treatment. So if I consider the sentence, it is at least 90% likely that more than half the sheep are black, this means that I can interpret this as having an outside epistemic probability. I believe with at least 90% that more than 50% of the elements are black. And here we now, for this we need a type 2 model. And now normally, so here we assume the uniform probability. On omega and Joe Halpern's more general framework, you then also need separate measures on every possible world. And then you can interpret on every single world the type 1 statement contained in it, see if this is true, and if this is true in at least 0.9, probably mu 0.9 of cases, then we can say the whole sentence is true. So much for the categorization of probability logic. Now, why is this important? This is important because we can use it to understand why statistical relational formalisms behave how they do. So let's have a look at how this works. So all the current approaches, with a possible exception of stochastic logic programs, actually fall into type 2 of this classification. They all define a probability measure on a set of possible worlds. This applies to Markov logic networks, which are then relational Bayesian networks, and probabilistic logic programs, for instance. There's one exception, which I wouldn't mention if I had not got some renewed attention recently, and those are stochastic logic programs. Stochastic logic programs are another probabilistic extension of logic programming that have been developed more than 20 years ago by Professor Muggleton in London, and which have been developed independently of probabilistic logic programming. And they have a very interesting semantics because the semantics is not defined via a possible worlds approach or even via a straightforward type 1 approach, but is actually defined as a distribution over proof trees, resolution proof trees of a logic program. And it has been argued that this is really a type 1 semantic. And one can see this as a type 1 semantic because proof trees can be seen as groundings. So with this exception, all the other approaches fall into type 2 of the classification. This is interesting because stochastic logic programs have been revisited recently with an attempt to integrate them with neural network-based approaches. And in my opinion, the fact that it has a type 1 leaning semantics is the reason why it works much better with that, because neural networks and deep learning approaches also do not follow a type 2 semantics. So let's look back at the challenges that we had outlined earlier. So we said that we have high computational complexity and unfavorable scaling behavior. And I argue that these two are actually related. So as domain size increases, the marginal probabilities often tend towards extremes. This is the problem with scaling. If our scaling behavior were fully understood, we could use sampling approaches to mitigate the computational complexity by shifting to a smaller sample and doing inference or learning on that sample, and then generalizing the results upwards by scaling them. We could overcome the computational complexity problem, at least approximately. But since the scaling behavior is poor, this approach does not work. So let's go in some more depth into this scaling behavior. Now, as domain size increases, the marginal probabilities of current approaches tend towards extremes. Now, if this works, I would like to quickly go to the drawing board to see how this might happen. So let's have a look at how we can go about this. So if we have a statistical relational approach, like probabilistic logic programming. I will not bore you with the details of how probabilistic logic programming works, but I will illustrate it in an example. Probabilistic logic programming models dependencies between different elements through an assumption of independent causation. So how do we model this? Let's say we have the smokers and friends model that we had earlier. So we have the idea that there is a certain likelihood P that any given person smokes. And then there's another likelihood that any given person is my friend. And now there's a third likelihood, R, that any given smoking friend will cause me to smoke also. Now, I wrote this now in a sort of Hohn clause way. The syntax, in case you ever want to look this up in probabilistic logic programming, is slightly different. It would be like this. In a prologue-inspired syntax. But in reality, all it is a Hohn clause, and it has a certain probability R. So, and we read this through an assumption of independent causation. Every smoking friend I have has a certain likelihood of causing me to smoke. But what does that mean? So the way this is actually interpreted internally in probabilistic logic programming is by randomly allocating the predicate smokes and friends independently for every domain element according to its probability. And then it also introduces another probabilistic term. So it introduces a probabilistic term for every X such that this is the likelihood that if X were to smoke and be my friend, he would cause me to smoke also. And then once we've introduced this auxiliary term, this reduces to a deterministic clause, and we get a typical standard clause, smoker, if smokes, friend, and the probabilistic auxiliary term is satisfied. Notice that, as usual, these are implicitly universally quantified, as is the case with prologue clauses. Now, what this means is that as the domain size gets bigger, the chance, well, as the domain size gets bigger, we can see quite quickly with a law of large numbers type argument that almost surely there will be an unbounded number of smoking friends as the domain size increases, and therefore the chance that none of them satisfy this probabilistic fact vanishes. So overall, as the domain size gets bigger, the probability that I smoke approaches 1. And the way one can see that this has to do with type 2 probabilities is to see this as a formula. So this can be seen as a first order formula, namely the formula for as there is an X such that smokes, friends, smokes of X, friends of X, and probabilistic of X. And we can see this as a first order formula, which is evaluated on random structures that are generated like this. And since this is the way probabilistic logic programming works in principle, reducing these things to random structures, we can see that this is the usual approach. Things will usually go to 0 or 1 because we have what is known as the 0-1 law, of finite model theory, which says that every first order property, every first order sentence is true either almost everywhere or almost nowhere in a random relational structure, where random means the structure gets arbitrarily large. This is a classical result of finite model theory that was developed by Chlebsky and Fagan in the late 60s, early 70s. So we have a general reason to believe that probabilistic logic programs will always converge to either 0 or 1, unless, of course, I have determinate clauses. So these are clauses that do not actually induce any quantifier here at all. These clauses also exist. So I could just, I could have another proposition here, of course. So I'm only smoker if I have the smoke gene. And then I could have a certain probability that I have the smoke gene. And then what will happen is that at the end, this will all just reduce to only having the smoke gene. This is asymptotic quantifier elimination. And that is a quite straightforwardly extracted from the proof of the 0-1 law. But you can, but essentially, if you will reduce all of it to constants, because then you wouldn't have sentences, but you can eliminate quantifiers. So this is a general problem. Now, what's actually going on here? In a real social network, it will not be the case if the more friends I have, I am doomed eventually to smoke. Instead, what is much more likely to happen is that I'm more likely to smoke the higher the proportion of my friends is that smokes. So that in the limit, my likelihood will just converge to the percentage of smokers among my friends. And we can prove using, well, the argument here that I gave, it gets a little bit more complicated. I published this in the TPLP paper last year. The argument is a little bit more complicated by the fact that you can have recursion in your logic program, but essentially this argument suffices to show that you cannot express anything like that in probabilistic logic programming. And similar arguments hold for the other formalisms of statistical relational AI that I have mentioned so far. So yeah, actually what you need to do for this actually to go through, we need the quantifier elimination, not for first order theory, but for fixed point formulas, because you get fixed point formulas from the recursion operator. But this is technical, we don't need this to go into this now. So this is the usual pattern for type 2 logics, because we have random structures determined by these probability measures, and then we have deterministic properties. Now, type 1 formulas also have a long history of asymptotic study. But while finite model theory studied type 2 formulas, even though they didn't know it, type 1 formulas were really studied by statistics and probability theory. And they are governed by something even more simple, the law of large numbers and the central limit theorem. As the domain size increases, the relative frequencies will not converge to 0 or 1, but they will converge to the values given by the parameters. So if instead of a probabilistic logic program, we had a way to state a dependency, a type 1 dependency within the program, then we could analyze its scaling behavior using statistics, which will converge dependent on the values given by the parameters. let's see. Now, yeah, I introduce in a submitted preprint, I introduce a formalism which is designed to achieve exactly that, called functional lifted Bayesian networks. So functional lifted Bayesian networks is based on a directed acyclic graph, much like these template models that I introduced here. But now for every relation R, we have a finite tuple of first order formulas. These express, well, in our simple case that we had here, they just express the fact that a friend smokes. And then for each of these formula, we make a continuous function that maps the frequencies of these formulas, the relative frequencies, and returns a probability. This is the bare bones of our type 3 logic. And then on any given domain, it will ground to a Bayesian network with underlying graph G, and the conditional probabilities given a structure on the parents is given by the function applied to the relative frequencies. So if we go back to our, example, let's say we have our smoking friends, then we would have a function we would have a function f smoker, which returns the proportion of friends that smoke. So this would then be the proportion of smokes given friends. And I mean, there are some boundary problems here. What if he has no friends at all? When we can't build this conditional probability, but that's not actually a problem in practice. The problem is exactly the same in probabilistic logic programming. It just assumes then that there is no one that smokes. So we could just set it 0 in that case. But what we then have is that in the limit, if the probability of smokes is set independently of the probability of friendship, as we did in the other, if the probability of smoking is set to be independent of the probability of friendship, as the domain size increases, f smoker will converge exactly to the probability set for smokes. Now, in this case, the probability that we induce is of the identity here, but we can have any continuous function. We can have a sigmoidal dependency. We can have any dependency at all. So we can put any continuous function here. And this seems a much more adequate model for this situation. So what does this actually give us? We can model a wide variety of such dependencies, as we've just illustrated, and we can actually combine it with classical quantifiers where needed. Since we have first order formulas here, we can actually still model the existential and the universal constraints. So we can combine it within one formalism with classical quantifiers that we have. Now, the bulk of the actual thrust of my paper is the understanding of the asymptotic behavior. So if we have an FLBN whose aggregation functions have a certain side condition, then it is asymptotically equivalent to what is called a quantifier-free lifted Bayesian network. What that really means is a network in which you have neither aggregation functions nor quantifiers, but that all you have are fixed probabilities or probabilities depending on formulas. So what you have are formulas and a deterministic and a probability depending on the formula. Why is this important? This is interesting because these quantifier-free formulas that come out at the end can be evaluated completely independently of the domain. So in the case that we had earlier, where me smoking depends only on other people's behavior and on no property of myself at all, this will just become a number. This number could depend on things I know about me, so it could depend on the type in logic of myself, the quantifier-free type of myself. But it cannot depend on anyone else, and therefore you can evaluate these directly independently of the domain size. We already got a result like this through asymptotic quantifier elimination for PLP, so where's the difference? The difference is that here, the equivalent network depends essentially on the supplied functions FR and the probabilities. So this is the example I just gave on paper. The probability will evaluate to a number depending essentially on FR and P. It will be FR applied to P. So if I want to learn the probability of P, or if more likely, given that I want to learn dependencies, I have a parametric family of functions FR, I can use the asymptotic limit to optimize the functions. If I want expectation maximization or any sort of algorithm at all, I do this on the asymptotic limit. And these can be estimated consistently from subsamples as a special case of projective families of distributions, which were studied in 2018 by Jäger and Schulte. There's also a newer Ichkai paper by the two on the similar topic, projectivity. And we can use this work to show that we can estimate these consistently. Right, so thank you very much. I would just like to conclude. So overall, what we get is that inspired by type 1, type 2, and type 3 characterizations from traditional probability logic, we can arrive at a formalism which tells us by its semantics how it will behave asymptotically. And we can guess, even though there's still technical work involved, we can guess how it will behave from the fact that it's fundamentally statistical, a type 1 formalism, or in a type 3 formalism with a frame of type 2, or whether it is a pure type 2 formalism which will behave in the way finite model theory tells us it will. And we can use this to address these fundamental problems in statistical relational AI. So thank you very much for your attention. I'm very happy to